Okay, welcome. This is the week 5 webinar for the class. And let me tell you the plan today. As always, I'll start out with Q&A. So any questions you might want to have, and throughout the webinar, of course, any questions you have are fine anytime. And then we're going to get into sampling distributions. So today is actually really the last day of the entire course where we just build machinery. But this machine is really important, and we're going to see some great uses of it. And pretty much for the rest of the entire course, we're just going to use statistics. So we're going to have the big theorem in a little bit. So we'll start out with what is a sampling distribution, and we'll see what that means. Then we'll get into what is an unbiased versus a biased estimator. And then the big theorem. And the big theorem for this entire course is the central limit theorem. And the central limit theorem really has 3 parts. The first part is the central limit theorem for means. So if the survey question is quantitative, then we can do the central limit theorem for means. The second is the central limit theorem for proportions. And similarly, if the first question is a yes/no question, then we can do the central limit theorem for proportions. And then finally, we can take the central limit theorem for sum. Sometimes it's more important to say, what is the total amount of all the answers instead of what is the average amount? And if we can do that, we can use the central limit theorem for sums. I want to mention something, give you a heads up, and that is what big thing is due on Sunday. Hopefully you all know. Yeah, project 1 is due on Sunday. So it's very important. You don't wait until Sunday to start doing that. That would be a disaster. Just let you know, Thursday at 8 a.m. is the last chance to send me a draft of your project. And I've already gotten some drafts, but those who haven't sent yet, you need to do that before 8 a.m. on Thursday. And then I will read it and I'll give lots of feedback on how to improve it. I want you to do well, but if I don't see your project first, before you do the final submission, then it's hard for me to tell you what you need to do. So it really helps to send it. And what I do is I read it read and give comments on a first sent, first reply basis. So if you send it at 7:59 a.m. on Thursday, I will read it, but it might be a while, because if I get, 12 other project emails, here's my project, that could be, over 100 pages of reading to read and then and write down suggestions and all that. And that could take a couple days even. So the earlier, the better. So just let you know that is a big deal. Also, if you have any questions on your project, you can post in the Project 1 discussion board, and I'll be happy to answer. Also, you can come to office hours. You can go get help from the tutor. And Kyle knows the best, but the other tutors can help too. And definitely help with the project. The project's, it's a decent part of the grade. Don't just say, I'm not going to do it. And you have to work in a group. It could be a group of 2, but it cannot be just you. If it's just you, I take off, I think it's like 30% or 25%, whatever it says in the syllabus. And that's really ugly. Basically, almost no one passes, gets a passing grade on the project who sends it in by themselves. So it's very important to make sure you have a group and work with your group. 3 is good, 2 is okay, 1's not okay. Okay. So are there any questions at all about anything? That's a good question. So the question is, are we turning in 1 for the group or each turn it in? The answer is you turn in 1 project. So one of you submits for your group, but make sure that when you do submit it, that all of your names are on the project. So I know who to give credit for. So that is important. That should be like on page 1. So you should have like a title page with your names on it and the title of the project. And then everyone gets the same score. I don't say, well, I like this person's name better, so I give more points. No, everyone gets the same score for the project. in the group. Okay, any other questions? Good question, very good question. Because I'm always happy to answer questions. Okay, if there are no questions, then I think I could do this one, but let me ask a different one. And again, this is going to be, no one gets to see the chat on YouTube, so you can answer it and don't have to worry about it being public. But let's see if you can tell me how many hours a week or how many hours of paid work did you work in the last 7 days? So I'm going to do that one instead of this one. So let me type that out. How many hours of paid work did you do in the last 7 days? Okay, and if you don't feel comfortable telling everyone, make something up that's reasonable. Don't say 1,000 hours. That's not possible. But my guess is everyone feels comfortable about how many hours they worked. Okay, and I'm just going to put in the answers, not say who did what, but just put them in. We have 5, 25. I want all of you to give me a number. 18, 31, 40, 34. Okay. All right. So that was a survey, right? All right. So now we got all these different numbers. And the next thing I want you to do is I want you to somewhat randomly, if you can randomly, if not, do your best, pick 3 of these numbers. Pick 3 of these numbers and find the average of those 3 numbers. Okay. And by the way, when there's just 3 numbers, it's easier to just add them up and divide by 3 than to use a fancy calculator, but you could use a fancy calculator. I want you to somewhat randomly pick 3 of these numbers, find an average, and post that in the chat box. So pick 3 numbers and give me your average. Okay. By the way, I'm just going to round the nearest whole number. That's easier because good enough for us. Okay. 32. Another 32. Okay, there should be one more, but as you work on it, I'm going to talk about this a little bit. We can also find the average of these numbers of the entire. We're going to call the people who came to the webinar today. You're the population, just for this particular example. So you are the population. We got a population of 6, not a big population, but I want to do it just as an idea. So you have a population of 6, and I can go ahead and now I can go to the calculator and go to the one variable stats calculator. And I can look at those numbers, and we can look at it as a population standard deviation because it's the population, and I can calculate. Okay, the mean was 25.5. All right, just a note, see if you remember, what symbol do we use for the mean? What's the symbol we use for the mean of the population? Yeah, mu. Yeah, and by the way, it's always okay to, on everything except for the project, to just spell it out, MEW or whatever. It's fine. For your project, you should make it all pretty and stuff, because on the project, you have as much time as you want, you get help and all that. So just a note in terms of that. but for answers to any questions on exams or discussion boards, MEW is just fine if you want. Okay, so the population mean is 25.5. So I'm going to write this down. And unlike you, I'm going to actually make it pretty because that's my job. So mu is 25.5. Okay, make that a little bigger. And also from here, we had the standard deviation is 11.471. And that's sigma, hopefully you remember that, equals 11.471. Any questions on first realizing we have a population of size 6, which is really tiny for what you usually do, but that's fine. We have a mean, mu, population mean that's 25.5. We have a sigma, which is a population standard deviation of about 11.471. All right. But these 21, 30, 16, 32, and 32, these, and the last one, by the way, was 35. These are also means. Are they mu's? What do you think? Yeah, these are not mu's. These are not population means. Because what you did is for each of these, you took a sample of size 3. Okay, these are sample means. Okay, do you remember the symbol we use for sample means? Yeah, X bar. Okay, so now I can go ahead and I can do, look at that one. Let's see, there it is. Yeah, bar X, so X bar. And say the, maybe, how about the third person said 18? And that was X bar. Any questions on that? Now, we can also find, you can also find the sample standard deviation. What letter do we use for sample standard deviation? Do you remember? The hint is this one's an easy one compared to all the others. What? Yeah, S. Everyone knows the letter S, I hope. Okay, and S was equal to, actually, I don't know what your S was, whoever had 18, but I'll just make something up. Let's say it might have been, I don't know, 4.2. Okay, again, I don't know what your S really was, but could have been that. Okay, let me make that a little bigger. So these are different, mu and sigma versus X bar and S. And I want to really emphasize what these are. Mu and sigma are the population mean and the population standard deviation. X bar and S are the sample mean and the sample standard deviation. And each one of you got a sample mean and a sample standard deviation. Any questions on that? Okay, so one of the things you might ask yourself is, if you have a sample mean, how far is it from the population mean, right? For this example, it's about, what, 7.5 away from the population mean. Okay, but in the real world, usually you don't know the population mean. Does that make sense? So if you do a survey of a bunch of Americans, for example, good luck finding the population of all Americans about something. But so what you want to do is you want to say, well, I don't know exactly how far the sample mean is from the population mean, because you want the population mean, which you can't get. So you use your sample mean to estimate, to say, this is my best guess of the population mean. But one of the big things you want to do is you want to say, well, how far away do I think that my best guess might be? So in other words, let's say you were in the business of doing surveys. Then every time you do a survey, your best guess is not going to be exactly the population mean. But maybe you could say on average, how far are my best guesses from the population means? Okay. And what tells you about, on average, how far something tends to be from something else? We've talked about this in chapter 2 in a big way. Here's a hint. It's a big part of the project 1. Yeah, it's a standard deviation. So it's a standard deviation gives you an idea of how far it might be. Does that make sense? Okay, now with a sample, that's different than just an individual number. With a sample, you can have a different best guess or standard deviation than with an individual number. And that's what we're about to get into. First, any question on this idea? Any question? Okay, one more thing that you might think about is, well, we have these sample means, 21, 30, 16, 32, 32, 35. If I looked at every possible sample mean that I could possibly get by grabbing 3 numbers out of these 6 numbers, okay, I don't want to waste your time. I'm not going to do it, but you can imagine doing it. Then here's a big question is, what do you think the mean of all these sample means might be? Any guess? The hint is I know it right away just by looking at the notes that we have in front of us. Yeah, it's going to be 25.5. So the mean of all the possible sample means that you could possibly get will be 25.5. All right, what do you think the standard deviation of all the possible sample means you could possibly get might be? Any guess? Yeah, I did this as a trick question, mostly so that we would remember not to make the mistake. It turns out it's not the population standard deviation. Okay, it is not the population standard deviation. And in fact, something that I did, I can go back to the actually pre-calculator. We can look at, say, a distribution. And what I did is I coded this up. And for example, we could have a skewed left distribution to start with. Okay, it has a mean and a standard deviation. Believe it or not, it just randomized a bunch of stuff. And what we can do is we can say, well, what if we have a sample of, let's say, size 36? Let's go 100, actually, just for fun. If we took a sample of size 100 and then another sample size 100 and then another sample size 100 out of this distribution, and then we looked at the distribution of all those samples of size 100, we could take a look at that. So let's do that. So notice we start out with a skewed left distribution because the tail's over on the left. But if I take samples of size 100, which does take the computer a couple seconds, it took 2,500 samples, each with size 100. Computers are very fast. No way could I do that by hand. And then it drew a histogram of all of the samples that it took. You can notice a few things. One is if you look at the mean of all the samples that it took, of all the sample means that it took, It's 298.23, which is very close to the population mean that was started with. Isn't that kind of cool? Standard deviation is not very close to the standard deviation of the population. We started out with something at 97.67, and now we're at about 9.68. It's much smaller. And in fact, it's smaller by about a factor of 10. Do you see that? Any questions on that? Okay, it's smaller than by about a factor of 10. And by the way, it's not a coincidence that if I take 100 and take a square root of 100, I get 10. And that gave me that. Okay. Also, we started with a skewed left distribution, but then when we took a histogram of all of these 2,500 different sample means, it's not skewed left anymore. What does it look kind of like? What's kind of the shape? Yeah, bell shape, but in our class, what do we use? What word do you use instead of bell? Yeah, normal. Okay, this is an approximately normal distribution. And it turns out that's always going to happen. If instead I looked at 36, then it's approximately normal distribution. It's not perfect, but it's approximately normal distribution. It's no longer skewed left. And if you take 97.67 and divide by the square root of 36, you get something that's not far from 16.12. Okay, so this is going to be the big theorem. Any questions at all on kind of this activity? If I do a new distribution, what I did is I can even make my own up. If I do user distribution, I'm going to call this Manhattan distribution, because I'm going to make it look like a big city. By the way, I made up the word Manhattan distribution, but it's a good one. Okay, there's another distribution. Okay, and if I take samples of size 100 from that, doesn't look like Manhattan distribution at all. It looks somewhat normal. Do you see how that works? If I take samples of size 2, then it doesn't look so normal anymore. It turns out you really need a pretty big sample size to get something that looks pretty normal. This looks really off from normal. It's got ups and downs and ups and downs and ups and downs. But with a big sample size, it does work. Any questions on this idea? Okay, so now let's continue on to some important stuff. So first is the distribution of all sample means with the same sample size is called the sampling distribution of the sample means. So it's called the sampling distribution. So there's going to be a bit of vocabulary today. So sampling distribution is one. If I put it in red, okay, or if I say it loud, sampling distribution, then that means that's an important word that you should know. And if you have any questions about what that means, I can help you out and give you more details. But hopefully it makes some sense. Okay, some symbols that we saw in the that little app that I showed you is the population mean of the sample means. Okay, so if you look at the sampling distribution and you look at all possible samples that you could take and take the mean of all the possible sample means, then that we use mu sub x bar, because mu is population mean, x bar is sample mean, so it's the population mean of all possible sample means. And that's the notation we use is mu sub x bar. Any questions on that? Okay, and again, it's fine when you're, writing out test answers and stuff or discussion board questions to use mu and then sub if you want, xbar or whatever, something like that is fine. Okay, the population standard deviation of all possible sample means is sigma sub x bar, because sigma is population standard deviation. X bar is sample means. So sigma sub X bar is a population standard deviation of all sample means. I know you want me to scroll. I'm not sure how much you want me to scroll. Was that enough, or do you want a whole lot of scrolling? You need to go all the way to the top, or? Okay, good. Wasn't sure what you needed to see. Yeah, so we got some new notation, and it's a little more complicated, but it really tells the story real well. Just a note, another word for the population standard deviation of all possible sample means, because that's a lot of words there, and it's used a whole lot, is also called the standard error. And you'll see that those two words used, standard error is a sigma sub X bar. That's just some vocabulary. Any questions? All right, so if we consider the collection of all possible sample means, okay, this is its own data set with a very, very large size, okay? Even with, if we just grab 3 out of 6, and we looked at, all possible collections of 3 out of 6, even that's not that tiny, it turns out. So that's what it's, it's 120 over 6. So even that will be 20 or so. But if you have, let's say you're looking at, the population of a size, let's say the Tahoe, which is around 25,000 people. And let's say you do a sample of size 40, and you look at all possible samples of size 40 out of 25,000. I know this sounds going to be weird, but it's such a big number, we don't have words for it. Okay, if I wrote it not in scientific notation, it wouldn't even fit on all of the lines of the computer. It's so, on a line of a computer, it's so big. Just let you know that. So we do this as an idea. We don't actually ever find all possible sample means. So it's more in just general. Okay, so it's going to be very large. Okay, but you can still think about it. Okay. So the sampling distribution, as I mentioned, is a statistics. For a statistic for the sample of size n is the distribution of all sample statistics for samples of size n. Okay, now comes the next one, which is important. A statistic is called an unbiased estimator for a parameter if the mean of the sampling distribution for that statistic is equal to that parameter. So for example, something I mentioned is that if you take the average or the mean of all possible sample means, you get the population mean. Okay, that makes it an unbiased estimator. So if I look at all the possible samples and look at the average of those samples, and I take the averages of those averages, I just get the population average. Okay, can you think of a statistic that is not unbiased? And by the way, if it's not unbiased, we say it's biased. Any guesses? Can you think of a statistic that's a biased estimator? And the hint is there's a lot of them. Don't see y'all jumping in. All right, let me give you an example that should be obvious. Okay, let's say I wanted to find out the range of people's heights in the world, okay? And let's say I did a sample of size 50 and looked at the range of the heights of those 50 people. Do you think that's a good estimate for the range of the population of Earth? Do you think the average of all the ranges of samples of size 50 for just people's heights will be equal to the range of heights in the world? What do you think? Yeah, definitely not. Think about the range of heights in the world. Remember, that would be the tallest person's height minus the shortest person's height. Okay, the tallest person's height is like going to be like 7'9" or something, or I don't know. I don't know exactly how tall the tallest person in the world is. The shortest person was just born, by the way, most likely, and they're going to be, you know, maybe less than a foot or something for the shortest person in the world. And you're going to get a gigantic range. Do you see that? But if you looked at just say 40 people and just randomly grabbed 40 people and saw the range, it's almost never going to be like over 6 feet tall. Does that make sense? So the range is an example of a very biased estimator. You should never use the sample range as a best guess for the population range. Does that make sense? Okay. On the other hand, the mean is your best guess if you have a random sample. Okay. Similarly, the proportion for the sample is going to be your best guess for the population proportion. Okay. And that'll be an unbiased estimator. So those are some biggies. The sum is also an unbiased estimator. Okay. Any questions on what unbiased estimator means? All right. Now comes the biggie, and that's the central limit theorem. So notice I put it in giant letters, big, bold. I'm going to say it loud. The central limit theorem. Okay, this is the most important theorem of all of statistics in any statistics class, even advanced statistics. There is no question about it. It is the biggie. And it says the following. Okay, the sampling distribution for sample means from samples of size n has mu sub x bar equals mu. So that means that the mean of all sample means is equal to the population mean. And sigma sub x bar is equal to sigma divided by the square root of n, where n is your sample size. Okay, so notice if you have a large sample size, sigma sub x bar is going to be very small. And that's what you want, because what you want is a good estimate for the population mean. So if your standard deviation is small, then it's very likely that your sample mean will be close to the population mean. If your standard deviation is large, then it's pretty likely your sample mean will be far from the population mean. And again, the whole point of doing a survey is to make a good guess of the population. So we want it to be close. So a large sample is better. Okay, here comes number 2. And that is if the population's distribution is normal, or if the sample size is large, and in our class and in most classes, our definition of large is going to be greater than 30. Where have you heard greater than 30 in this class before? Very important this week. That's a hint. Yeah, for the project. And I told you it was a subliminal message when I told you greater than 30 a while back, because you need it to be greater than 30 to have good data so that we can actually use this. Then the sampling distribution for the mean is also approximately normal. And we saw that in that little app that I did, where if you had a sample sizes of 100, then it did look pretty bell-shaped or pretty normal. But if you had a sample size of 2, it didn't look that normal. Do you remember that? So kind of in our class, we're going to use 30 as that boundary. Over 30, we're going to say approximately normal. 30 or less, not approximately normal. If you want to find out further details about this, like why it's not always 30, but for our class it will be, then I'm going to say it's a lot in this class. After this class, you need to take another statistics class. Like an advanced statistics class that has a lot of math in it. But for our class, we're just going to use 30. Sounds good? Over 30, we're going to let it be. We're going to say it's approximately normal. If you started out with normal, then you're still normal. But if you didn't, like skewed left or something, then over 30 to get approximately normal. Okay, and it's very important because if it's approximately normal, then that means we can actually do calculations because you can find probabilities if you know the distribution is normal, because then there's just some math. You can use my calculator or any normal distribution calculator, and you can find pretty much any probability you want to. If you don't know the distribution, you can't find probabilities. So we want it to be approximately normal. Any questions on this? Okay, and notice this works for any quantitative survey. Okay, all right. One thing that I didn't write in here, this is essential limit theorem, but it's real important to say that you don't have a biased sample. If you have a biased sample, you have useless data. Does that make sense? If you only asked your friends what their age is, that's not going to give you the average age of the population of America, because your friends are going to be probably close to your age. Does that make sense? So it's very important that you don't have bias in your study to be able to truly rely on the sample. Any questions about the central limit theorem, the most important theorem of all of statistics? Any questions? So I'm going to pause. I want you to read it again. So the central limit theorem is the biggie. And by the way, my office mate who also teaches statistics a lot just said, yes, yes, yes.
Yes, yes, yes.
But it's the biggie. Any questions? Okay, I like to use an example that actually will help you in your life financially. And maybe you're all billionaires, you don't really care anyway, but probably not. So I like to give an example where it does make a difference. Okay, so let's start out with this example. This is the easy one. Let's suppose you put $10,000 into the bank. Okay, what's the probability you're going to end up losing money after 1 year? Maybe you put it into Bank of America or something. Okay, so by the way, you lose money if X, which is the amount of money you made, is less than 0. Does that make sense? What's the probability of losing money in your bank account if you put it into like a big bank like Bank of America, Wells Fargo, or US Bank, or one of those? This should be really obvious. Yeah, it's 0. Okay, it's 0 because there's something called FDIC insured. If you didn't know what that is, that means that even if the bank went bankrupt, then actually the government will give you money back. So if you didn't know that, that's true. So the probability of losing money is 0. Okay, we're going to assume that America is still going to be America. That kind of the worst things will happen if we lose our country too. Okay, so the probability is 0. Is that clear? All right, but the interest rate, all right, the average interest rate in banks, by the way, is about 1%. Do you think that's good, by the way? 1% in a year? Not really, right? What's inflation, by the way? Yeah, a lot more than 1%, right? Inflation's a lot more than 1%. So, why is it that you're only getting 1%? There's a reason. Any guess? Okay, a couple things. One is not just doesn't lose money, it's really so the bank makes money. Okay, so the bank makes money on your money. Okay, that's the reason why you only get 1%. And I'm not saying banks are evil or anything, but it's a safe place to put your money. Okay, any questions so far? All right, so now let me do a different one. Okay, let's suppose instead that you put your $10,000 into a randomly selected stock in the stock market. Okay. And by the way, kind of in the last many years, the average percent increase of stock is about 9%, and the standard deviation is 20%. we could ask the same thing. What is the probability of losing money? Okay, this one you're not going to be able to do in your head, by the way. Okay, so a couple things. One is we're going to have to assume that the stock returns are normally distributed. Otherwise, we can't do this problem. It's not a perfect assumption, but we'll live with it for this one. So what's the probability that we're going to lose money? How do we do this? And the hint is this is from last week, but it's important. Any thoughts? Don't see y'all jumping in. We have a normal distribution. We want the probability that x is less than 0. We know the mean is 9, the standard deviation is 20. And we want to find the probability. So what we need to do is we need to go to the calculator. So let's go back. And we're going to use a normal probability calculator because we're assuming we have a normal distribution. If it's less than 0, well, the lowest less than 0 is negative infinity or negative 9999999. And the high will be 0. The mean was 9. And the standard deviation was 20. Any questions on that so far? Anyone lost? And we calculate. So what's the percent chance that you're going to lose money if you put it in the stock market with one stock? The hint is all you do is read and maybe do one little modification. Yeah, it's about a 32.64% or maybe about a 33% chance. I'll round to the nearest whole percent. So that is about a 0.33 or a 33% chance. All right. If this money is really important to you, and let's say this 10,000 is like the money you're going to need for tuition next year for college. Are you okay losing money and not having enough tuition to go to college? Yeah, probably not. This may not be the best idea. Yeah, on average, you're making a lot more than putting into the bank. Do you agree? But you have a 33% chance of losing money. So is there anything else you could do? The answer is yes. Okay, so here's another possibility. This is really important. Okay, suppose instead you put your $10,000 into a Dow Jones index fund, okay, which by the way has 30 stocks, okay. We can now say what's the probability of losing money, and we're going to make an assumption, which isn't perfect, but we're going to assume that Dow Jones is a representative sample and the stocks are independent of each other. Okay, and it's not perfect. If you want a little more representative, then you need to put it in some different stocks also. But this isn't an economics class, so I can't get involved. But I definitely know about this stuff in a deep way. Any questions so far? All right, so now what we can say, mu is 9, sigma is 20, but now we're not looking at a single stock. We're looking at an average of 30 stocks. Does that make sense? So if there's an average of 30 stocks, and we started with the normal distribution, means you still have a normal distribution. And if it was 31, then you don't have to even start with a normal distribution. Then what is the mean of all possible samples of size 30? The hint is this is very easy for this example. What's the mean of all possible samples of size 30? Yeah, it's still 9. It doesn't change. That's part of the central limit theorem, is that the mean is still 9. Okay, the standard deviation, on the other hand, what's standard deviation? Now we're going to do a little work. So the standard deviation, if you remember, is sigma over root n. So that's 20 divided by the square root of 30. And it's 30 because of 30 stocks. Any questions so far? And 20 over root 30, let's just calculate that out. Is about 3.6515. Notice the standard deviation went down a lot because we had a sample size of 30 that drops the standard deviation a lot, and that is important. Any questions on that? Okay, so now we can find out the probability that X bar is less than 0. Our low and the high will be the same. It's negative 99999 and 0 for the high to be less than 0. The mean is still 9, but my standard deviation now is a 3.6515. And I want to leave P blank. That's a point. There we go. Any questions on what I just did? And I hit calculate. Now look at the probability of losing money. What do you think? Now is it something that you really are worried about, or do you think it's not a very good, not a very high probability? What do you think? Yeah. Now it's really, really low. It's less than 1%, 0.0069. Okay, and that might be a risk you can take because now it's a really small chance of happening. See how that works? Okay. What they call this in economics, you might have heard of this. Anyone know what they call it? This kind of investment? No? Not, I'll tell you. It's called a diversified investment. Have you heard of that? Okay, if you haven't, you have now. It's called a diversified investment. This is not a statistics word. This is like an economics word or a business word. It's called a diversified investment. That means that each of the 30 stocks or each of the 30 things you invest in don't affect each other. So they are independent of each other. And it is important you have independence. Okay. So again, this is not a class on economics. I can't go further than that. But it's really important to understand the difference. Okay, so what this tells you is that if you have a choice to invest in the bank, to invest in a single stock, or to invest in a diversified investment like the Dow Jones Index Fund, and you want a really small chance of losing money, but you want to make good money, then the Dow Jones Index Fund is much better. It is definitely the best of the three. Do you see how that works? Because you still get an average of 9% return, but your probability of losing money, of getting less than 0, is almost nothing, by the way. Okay. By the way, if you're a gambler and you want to make a whole lot of money, then this is not a good investment because your probability of winning like 30% is really small. Does that make sense? Okay, so personally, do you think I ever invest in just single stocks? What's your thought? Okay, the answer is yes. And I call it play money. I only do it when if I lose money in that investment, it's not going to like hurt anyone. Okay, I mean, I'll be bummed a bit, but it's not like I'm not going to go to college or not going to be able to retire, that kind of stuff. On the other hand, for money that's important not to lose, things like college education fund, for my daughter, for example, she graduated a long time ago from college, but I did that, or my retirement fund. Then you want to have a diversified investment so you have a small chance of losing money. On the other hand, if you love gambling, then you don't want a diversified investment because you're not going to win the big, huge one. Do you see how that works? Okay, so the central limit theorem says that if you have a very large sample size, then you'll almost always end up with a mean that's equal to the population mean. And with investments, if the standard deviation is higher, it turns out you get a higher interest. And that's just how it works. Okay, so the next question, suppose instead I wanted my standard error to be equal to 2. So here my standard error was 3.6515. Do you see that? What if I wanted it to be equal to 2? So I wanted even a smaller standard error, so even a smaller chance of losing money. Do you see that? How big a sample size do I need? So what I can do is I can use the standard error formula that says the standard error is sigma over root n. Sigma for the stock market is 20. And I want 20 over the square root of n to be equal to 2. So what do I have to do? Algebra-wise. Now I need a little algebra. Nothing too terrible. And if you don't know, maybe I'll change this slightly, which it doesn't change anything, but just makes it easier to see. 2 is the same as 2 over 1, right? Hopefully you all know that. So if I have 20 over root n equals 2 over 1, what can I do? Any thoughts? I can multiply by 1 over 20, but I'm going to do what's going to be a lot easier. I can cross multiply. I could do 20 times 1, which is 20, equals 2 times root n. Hopefully you've seen that math. So that's called cross multiply. Yep, whenever you have two fractions equal to each other, you can always cross multiply. Okay, then I want n by itself, I want to get rid of the 2. So what can I do to both sides? Yeah, divide by 2. 20 divided by 2 is 10. Hopefully you can do that in your head too. That one's not too bad. Equals the square root of n. And now I want to get rid of the square root. How do you get rid of the square root? So how do I get rid of the square root? Any thoughts? How do you undo a square root? All right, if you don't know, you square both sides. You have power of 2 or square both sides. It's not times, it's a power of 2 or a square both sides. So if I square a 10, I get 100. If I square a square root of n, I get n. That's the whole point. So what that says, if I want my standard error to be equal to 2, I need to invest in 100 diversified stocks. Any questions on that? So a little bit of math, but not too much. Okay, let's move on. If we have a yes/no survey question. Okay, so what we've done so far is we talked about what happens if you have a quantitative survey question. So now it's what happens instead of quantitative, you have the yes/no question. So here's the central limit theorem, but now for proportions. And it says the following. Okay, we've seen this before. P is a population proportion. Remember that? we use P for the population proportion. Anyone know why we like in the population mean you use a Greek letter? Any guess on why we don't use a Greek letter for population proportion? We used to when I started teaching. It confused the hell out of everyone. So I don't anymore. Okay, and not just me, but no book uses it. I don't see it anywhere. Anyone know? What's the Greek letter for P? And the hint is you all know it. It's the only one everyone knows. Let's see y'all jumping in. Greek letter for P is pi. Yeah, and that's confusing as it can get. They used to use pi for population proportion. Everyone thought that was 3.14. So we don't do that anymore. So now we use P for population proportion, and they use P with a hat on top, which is, by the way, very difficult to type in Canvas. So PHAT is just fine. Okay. So P hat is a sample proportion. Okay. Q is 1 minus P. So if P is the probability of someone saying yes to the survey question, what is Q? What's that the probability of? Yeah, someone saying no. Do you see? Because that's how if like 40% say yes, then 60% say no. Or 0.4 is the probability of yes, 0.6 will be the probability of no. Okay, so Q, we're going to use that letter for 1 minus P. So by the way, today there's a lot of new letters. You notice that? So we're going to be using them a lot in this class for the rest of the quarter. So make sure you get these down. All right, so here's what the central limit theorem says. So sampling distribution for sample proportions for samples of size n first has mu sub p hat, which is the population mean of all possible sample proportions, is equal to the population proportion. Okay, which makes some sense. So let's say, I don't know, let's say that 45% of Americans like Joe Biden. And I surveyed, if we looked at every possible sample of size 100, then if you average all the proportions of those samples of size 100 that like Joe Biden, you get 45%. That's what this says. Okay, now comes the harder one, and that is sigma sub p hat is equal to the square root of PQ over N. So that's an important formula. Any questions on that? One major piece of this is there's an N in the denominator under the square root. So what that says is that whether you're doing means or proportions, raising the sample size influences the standard deviation in exactly the same way, whether you're using proportions or means, because you have that root N on the bottom. Okay, so if you have 100 times more of your larger sample, then that'll reduce your standard error by 10 times, because the square root of 100 is 10. Okay, whether it's proportions or means. And that's kind of the biggie. Any questions on this? Okay, so now the second piece, remember the second piece of the central limit for means was that if the sample size is greater than 30, then you have a normal distribution for the sampling distribution. Okay, that is not true for proportions. For proportions, it's different. And that is if you multiply n times p. So the number of, and n times p is the predicted number of yes answers, right? So if, say, 30% of the people answer yes for the population, and you have a sample size of 200, then n times p will be 60, because it would be 30% of 200 is 60, and that would be your predicted number of yes answers. And NQ, which is a predicted number of no answers, both have to be larger than 5. In this class, we're using 5 as our key number to be bigger than, You'll see occasionally, less often, 10 used. But in this class, we're going to use 5. And it's too complicated to get into all the details. So there's elementary stats. So 5 is our number when it comes to proportions. Okay, and it's not the sample size is bigger than 5. It's that NP and NQ are both bigger than 5. And if that's true, then the sampling distribution is approximately normal. Notice that in the central limit theorem for means, if you started with the normal distribution, then the sampling distribution is normal no matter what the sample size. When you have yes, no question, you can't start with a normal distribution. There's no such thing. When there's only 2 choices, that can't happen. But we're looking at the mean of all possible sample proportions. Each sample proportion is a number, and that is quantitative, and that's why this works. Okay, any questions so far? All right, I want you to put the following in the chat box. Oh, you're wanting to determine whether you can use the normal distribution. Because if you can't use the normal distribution, you're screwed. You'll never find any probability, right? Because you don't know what the distribution is. You see? If you can use the normal distribution, then you get to use the normal distribution calculator. See how that works? And the normal distribution calculator, hopefully I didn't make it too hard to use. Hopefully you can do that. Okay? But if you're not told the distribution, who knows? Good luck getting anything. Okay? So I want you to put this in the chat box. Basically, you are making a promise to me. Okay? And for those of you who are watching this on YouTube, I want you to say these words, and you're making a commitment. And that is, for a yes, no answer, I will not use the number 30 to see if the sample size is large enough. I want you to put that in the chat box. If you're watching on YouTube, I want you to say it out loud. There's a reason. So put it in. Everyone's got to put it in right now. You got to type it in. I'm making you do it. Give you a minute or two to do that. It's a little bit of typing. Okay, there's a reason I'm making you type this in. It is the biggest mistake students make in this entire class. So you made a promise, don't break your promise. If you break your promise, guess what's going to happen? Say on an exam. You break your pinky. I don't know about that. I won't do that. But you might rather me break your pinky than what I would do to you, depending on how important this class is. So what'll happen if you break your promise? Yeah, I will take off points. Okay, on any question where you have to, make that, where you have to look at that. Okay, you don't want to lose points. Okay, I'm doing this because this is the #1 mistake people make in the entire class. So don't make this mistake. I don't know how many times I can say it, but I'm trying to make you not make this mistake. Okay, if it's a yes, no survey question, you should always ask, what is the survey question? Will the person answering it say yes or no? Or will the data that I write be yes and no's instead of numbers? And if so, then you got to use, then you don't use the number 30. Then you're going to find NP and you're going to find NQ and make sure they're both bigger than 5. All right, so let's do a real one. One of the nice things about from now on for the rest of this entire course, I could just go in the news and I can look for something on CNN or whatever it is, and I can use it for the class because that's how important this class is. It's used everywhere. So I went to CNN, so one of the typical news stations, and what it had in one of the articles that they had, one of the news articles, was fewer than half of all Americans say that voting in elections is a highly effective way to change the country for the better. Isn't that sad? Okay. So it's kind of sad. I don't have an answer to make it better. But voting is still a good thing, even if you don't think it's going to help make it better. It's not going to make it worse. So you should definitely vote. Okay. And the sample size was 8,480. Okay. First thing, is this a quantitative survey question or is this a qualitative survey question? Okay. Is this a quantitative or is this a yes/no survey question for what CNN what they asked? Okay. And actually, it was the CNN quoted Pew's research. Is this a yes/no or is this quantitative? Yeah, this is yes/no because the survey question they asked people, or I guess as they asked people, is do you think that voting in elections is a highly effective way to change the country for the better? And if I asked you, either say yes or no. Those are your choices. You don't say 73. Does that make sense? So that's a yes/no survey question. Okay. So now here's something we want to find out. Let's this. Okay. So from the survey of 8,480 Americans, by the way, is that a large sample size? Right? There's like over 300 million Americans. Do you think 8,480 is large? What do you think? Given that there's, hundreds of millions of Americans? You could look at only adults if you want. Still over 100 million, a couple 100 million. Okay. So it turns out this is one of the things that I'm hoping to learn in this class is actually this is a very large sample size. Okay. And we're going to see why in a bit. Okay. And then next week, we're really going to see it. Okay. So from the survey, it turns out 44% said that it is highly effective. Okay. That voting in the elections is a highly effective way to change the country for the better. So the question I have is, do we think that under the majority, less than a majority of Americans think that it's highly effective? Okay. Well, we got 44% of this 8,480. Do you see? But 8,480 is tiny compared to the whole population of America, right? So here's the way we're going to be looking at this. And this is how you use statistics in just about any research project. And you turn it into something slightly different. You say, if it was 50%, because that means that it's not under 50%. So I want to see, is CNN wrong? Because CNN said, fewer than half. So what if it was 50%, which is like kind of the smallest number that's not fewer than half? So if 50% of all Americans think that voting in elections is a highly effective way to change the country for the better, then what is the probability that a randomly selected 8,480 Americans, at most 44% of them, think that voting in elections is a highly effective way to change the country for the better? It's a lot of writing. Any questions on what this is saying? Okay, so the first thing we need to do is want to say, well, we want to find a probability. So can we use a normal distribution to do that? And from the central limit theorem, in order to use a normal distribution, we have to have NP and NQ bigger than 5. Any questions on that so far? So NP is 8,480. And then times P, so that's N is 8,480. P is 0.5. Because we're making that assumption that 50% of all Americans think that voting in elections is highly effective. And fortunately, I can do this in my head. That's 4,240. Is that bigger than 5? Yeah, you better know that. Yeah, that's a lot bigger than 5. I'm going to do double greater than. That means super bigger than 5. No issues. NQ in a similar way, that's going to be 8,480 times, and I'm going to write 1 minus 0.5 just to remind you that Q is 1 minus P. 1 minus 0.5 is still 0.5, and you still get 4,240, which is much bigger than 5. Any questions so far? Okay, so because of that, the central limit theorem, now that we got bigger than 5, says the sampling distribution is approximately normal. So now I can write p hat has a normal distribution. And if it's much, much bigger than 5, it's very normal. Okay, it is so close to perfectly normal that you don't have any worries at all. Okay, and then it says that mu sub p hat equals p. And our assumption is that p is 50% or 0.5. So in our distribution, we're going to have 0.5 as the mean. The standard deviation is PQ over N. P is 0.5. Q is 1 minus 0.5. And N was 8,480. Any questions so far? So we need to answer 1 or 2 to decide if it's normal to do, or do we need to answer both? When you say 1 or 2, do you mean NP and NQ? Does that mean by 1 and 2? So you need to have both NP and NQ bigger than 5 to have it to be normal when you have a yes, no. Yeah, and then the other thing, which is true of everything we do in the entire class, is you can't have bias. Does that make sense? Yeah. So if you only asked Republicans, then that would be biased. Or if you only ask Democrats, that would be biased also. Do you see? Because they tend to have different attitudes about voting. Do you see that? So NP and NQ are, they both need to be bigger than 5, and you have to have no bias, or do your best to limit bias. Any questions on that? Any questions? Okay, so now what we do is we figure this out. We need the square root of 0.5. 1 minus 0.5 just happens to be 0.5. It won't always be the same number, by the way, over 8,480. So now let's do it. Let's take the square root of a fraction. And that's 0.5 times 0.5. That's right. It's yeah, over 8,400. There we go. And you get 0.005455. So I'm just going to write equals n 0.5, comma 0.005455, like that. The low, by the way, Okay, so again, what we want to find out is what's the probability of randomly selected 8,480 Americans having at most 44%. So the low, you can call it 0 or negative 99999. I can go negative 99999 because we're assuming normal distribution. It doesn't make any difference, actually. You'll get the same answer. And the high will be 44% or 0.44. Any questions on that? So now we have a low of negative 9999 with a high of 0.44. We have the mean was 0.5. We have the standard deviation was 0. It's easier to just copy and paste this big number. 0.005455, etc. And our probability is pretty much 0. 0 to as many decimal places as this calculator can even handle. Okay, so what do you think? They only asked 8,480 Americans out of the entire population of America. Probability is basically 0. So do you think CNN was right saying fewer than half of all Americans say voting in elections is a highly effective way to change the country for the better? Okay, and the answer is absolutely, because probability of them being wrong is so small that they're not wrong. Do you see how that works? Any questions on this? Okay, this is how statistics is mostly used, actually, is you find these probabilities, and if it's so small, then you say that your assumption, in this case, that it was 50%, it must be wrong, so it is less than 50%. Do you see? Any questions on this example, which is a main type of example? All right, now let's do the last central limit theorem, and that is the central limit theorem for sums. And that turns out to be really similar to central limit theorem for means, but yet if you think about, if you take an average and you want the total, you multiply the average by how many people you surveyed, and that gives you the total. Because remember that you find an average by taking the total and dividing by n. So you find the total by taking the average and multiply by n. Do you see how that works? Basically, the rest is just saying that. So the sampling distribution of sample sums from samples of size n has mu sub, this is something might be new to you, that this is actually a capital sigma. And that's the letter that mathematicians use to say sum or the total. So mu sub sum of x, or capital sigma of x, is equal to n times mu. And sigma, so lowercase sigma, this population standard deviation of all possible sums, is equal to the population standard deviation times the square root of n. So different formulas now. Okay, if the population distribution is normal, or if the sample size is large, greater than 30, then the sampling distribution for sums is also normal. So notice that to decide if you have a normal distribution for the sampling distribution, whether you're doing sums or means, it's exactly the same. No difference. Proportions are different. Means and sums are exactly the same as each other. Any questions on that? Okay, let me give you an example of why you might care about the sums more than the means. Let's suppose you own a restaurant. Okay, maybe some of you do. I don't know, but probably not. But you never know. Let's suppose you own a restaurant, and let's suppose the average customer at your restaurant spends $33.23. Okay, that's how much they spend at your restaurant. Okay, and the standard deviation is $9.22. Okay. If 65 customers eat at the restaurant today, what's the probability that the total revenue for the restaurant will be less than $2,000? Okay. So if you're the owner of a restaurant, you care about the total revenue. You don't care about the average. You want the total, right? It's how much money you're bringing in. Does that make sense? Not how much per person, but just how much from the end of the day. Is that clear? So total in that case is much more important than average. Okay, and also, what is the first quartile for the total revenue for a day? Okay, and one reason why you might want to know what's the probability is going to be less than 2,000. Well, if you have to pay your staff $2,000, then if it's less than 2,000 for your revenue, you're in trouble, right? So that means everyone's gonna be pissed at you. Everyone's gonna like quit the job because you can't pay them. And no one's okay with not getting paid for their work, right? So this is an example that's kind of real life business. Okay. And the first quartile would be, 25% of the days are going to be less than how much money for revenue. So it's going to be kind of a bad day. You can look at it that way. Okay, so we're going to start out by, notice, by the way, we have 65 customers. Why is the number 65 important and big enough? Yeah, it's larger than 30. We're back to the quantitative, so it's larger than 30. So that means that we do have a normal distribution. The mean is going to be 65 times $33.23. And the standard deviation is going to be the square root. It's going to be, sigma. So sigma now was 922. And then times, and then we're going to do the square root of n, and n is 65. Okay, 65 times 3323 is 21.59 and 95 cents. I'm going to put that in for the mean. And then we have the 9.22 times root 65. And that's $74.17 and a little tiny more. So I can put that in for the standard deviation. Any questions so far? So please ask if you have any questions. Okay, now the first question is, what's the probability to be less than 2,000? Okay, so less than 2,000. The low, we can call it negative 99999. Could call it 0. It won't make a difference in this case. And 2,000 was the high. Probability is what we want. And we have, looks like about a 1.6% chance or so. So the probability is about 0.0155. Okay, a little less than 2% chance. Okay, that's not too high. That might be small enough. What's the first quartile? How do I find the first quartile? What do I have to change here? There's two things I have to change. Yeah, P. What's P? Yeah, 0.25. What else do I have to change? Here's a hint. If I hit calculate, it says, please leave one of these boxes blank. What do I have to leave blank? Yeah, I have to leave the high blank. And now I can hit calculate, and I'm going to do the nearest penny, $2,109.92. 2,109.92. Good. Okay, so the first quartile, $2,109.92. Okay, so 25% of the days, you're gonna make no more than $2,109.90. The other 75% of the days, the rest will make more than that. Do you see how that works? Any questions on using the central limit theorem for sums? Yeah, I want to let you know one of the hardest parts, and my definition of hard, by the way, is my students get it wrong. Don't you think that's a good definition of hard? My definition of easy is almost everyone gets it right. So one of the hardest parts about this chapter, okay, and it continues, by the way, throughout the course, is identifying whether to use the central limit theorem for means, central limit theorem for proportions, or the central limit theorem for sums. Okay. And the way you do that, first thing, if it's a yes/no question, then it's a central limit theorem for proportions. So think about the survey question, what data you're going to be writing out in the, as the answers. And so a bunch of yes and no's kind of thing, then it's proportions. If it's numbers, then you have to think about, well, am I interested in the total or the average? If you're interested in the average, then it's for means. If you're interested in the sums, then in the total, then it's for sums. So you have to get those three straight. Okay. And nowhere do I say you have to memorize any formulas. But if you don't know which formula to use and you use the wrong one, it will go very poorly for you. So it's really important to be able to see the situation and be able to use the right formula. Does that make sense? Okay, what's the final thing I have to do today? The secret word. Secret word is root. Okay, not because you're rooting for your favorite team in the baseball game, but because if you look at the central limit theorem, for the standard deviation, there's a root n here. For proportions, there's a root here. For means, there's a root here. It's a big P sawable. All three of them. In fact, there's a root n, but I just did root. Okay, so that is pretty much everything I want to talk about. I want to let you know, don't wait till the last minute to do your project and turn it in. Turning your project at 10 p.m., that's when things can go wrong. And if you say I need an extension, I don't give extensions on the project. So you'll just be crying. So make sure that you don't wait until like Sunday late night to submit the project. Okay, you've had weeks to do it. So 21 days versus 20 days doesn't really make a difference in terms of how much time you have. So think about it that way. And also make sure that by Thursday before 8 a.m., if you haven't already submitted your project rough draft, then make sure you have that submitted. Better is Wednesday, so that way you'll be one of the earlier ones to get feedback from me. Okay. I do, just to let you know, Wednesday, I am busy almost all day teaching and meetings. So if you send it to me Wednesday, then I'll probably get it back to you Thursday morning. So don't get mad at me if it takes a day. But Thursday, I have very little on my calendar. So I'll be working, Thursday in reading your projects and giving feedback. If you send it today, then I'll probably get it to you by tonight or maybe tomorrow. Okay. Any questions? Let me stop the recording.